The Mythical Math Kingdom. Once upon a time, in a world far, far away, there was a village of people who all loved numbers, and they all represented different parts of a number. And they were all ruled by a king and queen, and the king and queen decided to name this village the Mythical Math Kingdom. Now, each person or part of the village represented a different number. For example, the king and queen represented whole numbers, the bakers or the cooks represented fractions, the maid and butler represented decimals, and the townspeople represented integers. Now, the king and queen were whole numbers, and in this village they lived on the number 1. Whole numbers are counting numbers, including the number 0, and I assigned the king and queen whole numbers because I believe whole numbers are the easiest number to work with. And king and queens are like the rulers of a village, just like whole numbers in my world or in my head rule. Next we have the maid and the butler, and in this story they represent decimals. Decimals are like trailing numbers, and they start trailing after the decimal point, which is after the ones place in the base 10 system. Just like maids and butlers would trail after a king and queen, the decimals trail after a number. Next we have the townspeople, which represent integers, which are counting numbers, including 0, and they include negative numbers. Now, townspeople are below the king and queen in a village setting, just like this negative number, -1, is behind 1, which is where the king and queen live. Next we have the joker, which represents fractions. Fractions, in my opinion, are one of the hardest numbers to work with, just like jokers can be tricky and hard to work with. But sometimes they're nice enough and let you go, and they end up actually working out very nicely. Now, Matt and Kelly lived in the Mythical Math Kingdom, and today they went to school to learn all about numbers. They're excited to learn about the different parts of numbers, even though they know it can be tricky yet sometimes. First, their teacher teaches them the different parts or jobs which represent whole numbers. Like I said before, the kings and queens represent whole numbers in this world. To place them on a number line, you place the tally marks equally spaced starting at 0. And for this example, the king and queen of Mythical Math Kingdom live on number 1. The king and queen of the village next door, the Mysterious Math Kingdom, live on spot number 2, and so on. Next, we have decimals, which you split the distance between each number. So for this example, between 1 and 2, you split them into 10 equal pieces, which would be called tenths. In this example, the king and queen are on number 1, and the maid and butler, number 1, represent 1.1. So that is the king and queen representing number 1, and then the 0.1, which is a tenth, would represent the first maid or butler. 1.2 would represent if there was a second maid or butler, and 1.3 would represent if there were 3 maids or butlers just trailing after the king and queen. And it can go on and on. We can even have an infinite number of decimals, so there could be 1.102345, and that would be all the amounts of maids or butlers trailing after the king and queen. It can go on forever, pretty much. Next are integers, which are any numbers that don't have a fractional or decimal value, which includes negative numbers. I chose to have these integers represent the villagers because integers include negative numbers, and villagers are people that are below a king or queen status level. So villager number 1 would be -1, or would live on -1 on the number line. Villager number 2 would be -2 on the number line, and it can go on forever, just like decimals. Fractions are a ratio of 2 whole numbers where the denominator does not equal 0 and the numerator is less than or equal to or greater than the denominator. And in this case, like I said before, fractions represent the joker. In this case, between 2 and 3, which would be the different whole numbers, it is split into equal parts of 10. So on the first point, like I show here, it's 2 and 1/10. And then it goes 2 and 2/10, 2 and 3/10, 2 and 4/10, and so on. And not all fractions are created equal, so in order to be able to compare them and combine them, we have to find or make common denominators. So I said before, fractions can be tricky to work with, but if you if you make them all equal to each other, in this case 1/2, we have 1/2 and 2/3. If you make common denominators, which between these two it would be number 6, it's easy to work with, and you can see that 2/3 is greater than 1/2. So as long as you get the hang of making sure there's common denominators or trying to find the easiest way to work with fractions, they're not that difficult. So just like how all people are not the same, all numbers are not the same, but there can be many parts of a number, just like there are many parts of a kingdom. All these parts work together to reach a common goal. For example, there are small and large numbers which show us different size amounts, like populations, or the number of kings and queens there are in a kingdom. There are also parts of a whole number, or decimals, which trail after the ones place, or the base 10, like decimal place, of a number. Knowing where each part of a number lives on a number line, it helps us to remember that there can be many parts to a system, or in this case, a kingdom. And all these parts have to work together in order to have a smoothly running kingdom or system. Next, the teacher talks to Matt and Kelly about decimals. The decimals, you can represent them or picture them as a base 10 system, which is up on the top left corner. This image shows the base 10 as the decimal place, and we are pretty much just dividing by 10 each time to get a new decimal place or decimal value. So you can start at 10, divide by 10 to get to the ones place, divide by 10 again to get to the 10th place, and divide by 10 again to get to the 100th place, and each are broken up again and split 10 more times. And this goes same with the math drawings. We can see decimals in a math drawing. So you have 1 whole meter, and then if you want to get to decimeters, you divide the 1 by 10 to get 10 tenths of 1 meter equals 1 meter. And then you can divide that 10 by 10 again to get 100 hundredths of a meter. Now, math drawings are kind of the same as bundling. Bundling, you start with different amounts of the tiny little squares, so that can represent 1, that could represent 0.1, that could represent 0.01. You just have to make sure that you state which amount these account for. So in this case, the tiny little squares represent 1, and 10 of those single squares gives you a 10, which is the stick, which is 10 squares, and then it can represent the big square, which is 10 of the sticks, which is made up of 10 of the single ones. So there's 100 little ones in that huge square. And along with decimals, you can round, and in this case we have 0.1389. We round it to the nearest thousandth. I pointed out here 0.1, the 1 is the 10th, the 3 is the 100th, and the 8 is the 1000th. And we want to round to the nearest thousandth. So we see that there is a 9, and if the number is greater than 5, that means you round up, round the number up. So we look to the right, see the 9, and we see the 8, so that means we round that 8 up to a 9 to get 0.139. Now, if instead of there was that 9 there at the original number, if that was a 4, then we would round down, is what it's called, but in reality it would just stay at the 0.138. Next, we have large numbers. An easy way to make sense of a large number, like 20 million, is to make bundles or math drawings. In this case, one of the sticks represents 1 million, So then 10 of those sticks would make a huge bundle, which would be 10 million. This helps us represent large numbers like 20 million. Or we can write it in scientific notation, which is rewriting the number like this. So we have 20 million, and we see that there's 7 zeros. Now all numbers are part of the base 10 system, so if we do 10 to the 7th, which is the exponent, if we do 2 times 10 to the 7th, that means it's 2 with 7 zeros trailing after it, which is 20 million. Large numbers are used for a variety of things like budgets or population sizes, or even debt. Comparing these large numbers helps us know which option is either more realistic, which lets us make or obtain the most, etc. Mostly large numbers are used for big corporations, and in this case it would be like how much the mythical math kingdom is worth. Next is fractions, comparing fractions. So there's different ways to do this, and one of the first ways you can compare fractions is by looking at the denominators. You have to ask yourself, are they the same? If not, which one is smaller? Which one is larger? And then, after looking at the denominators, you have to look at the numerators, which helps us determine if they do have the same denominators, like in this case 5/9 or 4/9. It'll help us see which one is larger. 5 is larger than 4, so 5/9 would be larger than 4/9. Or you can convert them into decimals, which is where you divide the numerator by the denominator and then compare them. Other methods to compare fractions would be to draw a math drawing or place them on a number line. In this case, we can see that 5/9 is greater than 4/9 because 5 shades or takes up more parts of the whole 9. And this works for any fraction. It doesn't just have to be ninths. It could be anything, really. Next, the teacher talks about arithmetic operations. There's traditional and non-traditional arithmetic operations. And for addition, the traditional one is just combining X amount of units to an object. Subtraction is taking away X amount of units from an object. Multiplication is repeated addition, but when multiplying by 0, the total is 0. And division is the inverse operation of multiplication. Now there's different arithmetic operations, and those include associative property of addition and multiplication, commutative property of addition and multiplication, and distributive property. Associative property allows us to move parentheses, and even when we do this, the total or the whole amount will stay the same. That works for both addition and multiplication. We just shift the parentheses over to the left or right or wherever it needs to go. Commutative property says that if we flip the numbers, like we have a plus b, it would equal b plus a because the numbers are staying the same. They're just switching spots. And again, that works for both addition and multiplication. The distributive property is a little unique, and that is where you have a group of numbers inside of parentheses and a number outside the parenthesis, and you distribute it to each of the numbers that is in the parenthesis. So in this case, we have a times b plus c, so then we get ab plus ac. And either way, even if we do b plus c first and then multiply by a, it would all equal the same amount. So now, after Matt and Kelly learned all about different parts of numbers, the teacher assigned them multiple questions to answer before class the next day. The first one is, the queen goes to her favorite restaurant and her bill is $43.57, and she wants to leave a 20% tip. How much money should she leave? After knowing different parts of numbers, Matt and Kelly decide that the easiest way to calculate this would be to do a percent table. They know 100% of the amount is $43.57. Because of the base 10 system, they know that 10% times 10 would equal 100%. So if you move the decimal place 1 to the left, that would equal 10%, which is $4 or 4.357. And then 20% is just 10% plus 10%, or 4.357 plus 4.357. So that would mean that the queen, if she wants to leave a 20% tip, she would have to leave $8.71. On to number 2. 1 serving of colorful cereal gives the king 2/5 of his daily dose of vitamin B12. How much should he eat to receive his full daily dose of vitamin B12? Now this can be a tricky one, but after talking about how to compare fractions, Matt and Kelly decide the easiest way to go about is to draw a math drawing. So they draw a rectangle and space it into 5 equal groups, and they know that 1 serving is 2/5. So they shade in 2 of the 5 rectangles, and 2 servings would be an additional 2 squares out of the total 5. So if he wants to get his full daily dose of vitamin B12, he would have to eat 2.5 servings of the colorful cereal. On to number 3. 1 serving of colorful cereal gives the king 12% of vitamin C. The king ate 3.5 servings of cereal. How much vitamin C did the king get by eating 3.5 servings of cereal? Solved by math diagram. And also mentally calculate 3.5 times 12 without a calculator. If 1 serving equals 12%, then a second serving would be an additional 12, a third serving would be an additional 12, and then we would need another half. Half of 12 is 6, so 12 plus 12 plus 12 plus 6 equals 42%. And that is shown by both the math drawing and the mental calculations. Number 4. A group of the villagers decided they will donate 3/4 of the money in their pockets right now to a charity. The amount of money in their pockets is listed below. Write a set of equations that will show how much money this group will donate. The farmer has $10, the male guard has $12.30, the female guard has $15.70, and the construction worker has $11. So to do this, Matt and Kelly decided to do 3/4 times 10 plus 1230 plus 1570 plus 11, and they used distributive property to distribute 3/4 to all of the numbers and got the totals, added all those up, and got $36.76 that all these people would donate to charity. On to number 5. A road crew is building a new road for the kingdom. So far, 2/3 of the road has been completed, and this portion of the road is 3/4 of a mile long. How long will the completed road be? When the road is 1 mile long, what fraction of the road will be complete? Matt and Kelly thought the best way to do this would be to draw a double number line. So the portion of the road and the length are the 2 different parts of the number line, and 2/3 of the road is 3/4 of a mile long. Now, as they remembered from learning in class before, the easiest way to work with fractions is to make them have common denominators. So in this case, they split the number line into eighths. So 3/4 of a mile is also 6/8. So then when they get to 1 mile, which is 8 out of 8, that would equal 8/9 of the portion of road. It's also shown down by the math drawing where they split a whole rectangle into 4ths, shaded 3 of them in to represent 3/4 of a mile long, and split that big rectangle into thirds, and 2/3 of the 3/4 is 8 pieces. So 8 pieces is in the 2/3, so 9/8 miles in total. Number 6. The farmer picked half a gallon of blueberries. He poured the blueberries into one of his plastic containers and noticed that the berries filled the container 2/3 full. How many of the farmer's containers will 1 gallon of blueberries fill? How many gallons of blueberries does it take to fill the farmer's container completely full? How many of the farmer's containers will 2 gallons of blueberries fill? And if the farmer wants to give his friend 1/4 a gallon of the 2 gallons of his blueberries that he still has, how much of his container should the farmer give his friend? So Matt and Kelly decided to draw a math diagram again. So the whole rectangle represents 1 gallon. And the farmer picked 1/2 a gallon of blueberries, so that is shown in the math diagram. And 1/2 a gallon of blueberries fills the container 2/3 full. So in each 1/2 gallon, 2/3 is shown. So in a whole gallon, 4/3 of a container would be full. So with 1 gallon of blueberries, there will be 1 1/3 containers full. The next part is how many gallons of blueberries does it take to fill the farmer's container completely full? I just answered that one, never mind. So then how many of the farmer's containers will 2 gallons of blueberries fill? They do the 4/3 times 2, which is 8/3, which would equal 2 2/3. And the farmer wants to give his friend 1/4 a gallon of the 2 gallons, so it would be 8/3 times 1/4, which would be 8/12 or 2/3. So he would give his friends 2/3 of the blueberries. No, of the container of blueberries. Number 7. A local hot dog stand sold 3/8 of its hot dogs before noon and 2/5 of the remaining hot dogs after noon. The stand sold 300 hot dogs in all. Solve the problem below only using a math diagram. How many hot dogs were there at first, and how many hot dogs were left? So 3/8 shows us that there would be 8 parts of the whole. So Matt and Kelly drew a big rectangle and split it into 8 pieces. They showed the 3/8 that was used before noon and the 2/5 that was used after noon, and then that gives us what is remaining left. So 3 of the 8 pieces were left. And since we know that they sold 300 hot dogs in all, 300 divided by 5 is 60, so each piece would have 60 pieces because each are equal to each other. So the remaining amount of hot dogs would be 60 times 3, which is those white pieces. So 180 hot dogs would be remaining, and they would have started with 480, because you would add the 300 that they sold plus the 180 hot dogs that were remaining to get 480. Number 8. The farmer planted 65% of his farmland with onions, 20% of his land with cotton, and the rest with soybeans. The soybeans are on 90 acres of land. How many acres of farmland does each farmer have? Solve this problem in 3 different ways, one of which must be a strip diagram. So Matt and Kelly decided to do the strip diagram, which is in the bottom left, the percent table, which is the top one, and then a table, which is the bottom right. So 100% would equal 15% plus 20% plus 65%. We know that 15%, which would be the soybeans, because 65% plus 20% gives you 85%, so you need 15 more to get to 100. So the 15% equals 90, and then if you divide that by 3, you get 5%, which would be 30 acres. If you multiply that by 2, you get 10%, which would be 60 acres. And then if you multiply that by 5, 50% is 300. So 100% would equal the 90 acres, which we know are the soybeans, plus 60% plus 60%, which would equal the cotton, because cotton is 20%, and then plus, in parentheses, 300 plus 60 plus 30, because you do 50% plus 10% plus 5%. So you'd get 90 plus 120 plus 390, which would be 600. So 600 acres in all. You can see that's shown by the other two different ways as well. Number 9. A shirt was on sale for $24.45, and this was 23% discount from the original price. What was the original price? So 23% was the discount. So in order to find the missing percent, I would say, you would subtract the 23% from 100%, and that gives you 77% of the original price equals the sale price. So in order to make a percent a decimal, you put the percentage amount over 100, divide that, and you would get 0.77. So we can put that into an equation, which would be 0.77 times the original price equals the sale price, which is $24.45. You subtract that out to get the original price by its own. So $24.45 divided by 0.77, which is shown to the right in long division. And we get that the original price was $31.75. Now, in the long division, you see that the numbers were changed to whole numbers, and that is possible by the base 10 system as long as you multiply it or put the decimal point back where the original numbers would be. So number 10. If 2 1/3 pints of jelly filled 3 1/2 jars, then how many jars will the farmer need for 15 pints of jelly? Will the last jar be completely full? If not, how full will it be? So, there is a math drawing here that Matt and Kelly decided to draw. So 2 1/3 pints equals 3 1/2 jars. So Matt and Kelly just drew that over and over again, which 7 pieces would equal 3 1/2 jars. So they did that multiple times until they reached or got to 15, and there was a little bit past 15, you got to 16 1/3. And since we only want 15 pints of jelly, 16 1/3 is too much. So 1 pint of jelly is 2/3 of a jar. So we have 21 pieces total, which that would be 14 times 7, 21, no. There's 21 pieces total out of like adding the 3 1/2 plus 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 3 1/2. Then we would have to add 2/3 of a jar in order to get 21 2/3 jars for 15 pints of jelly. Number 11. If a cake recipe calls for half a cup of butter, and a cake recipe calls for half cup of butter, so a half cup of butter equals 1 cake, or goes into 1 cake. If you had 2 1/3 cup of butter, how many cakes can you make? So we have 2 1/3, which you put that into a mixed or improper fraction, and we have to create common denominators in order for them to be equal, in order for them to be workable. So 2 1/3 equals 7/3, so we multiply that by 2 to get 14 over 6. And 1/2 is also equal to 3/6, so 14/6 divided by 3/6 gives you 11/6, or 1 5/6 cakes you can make with 2 1/3 cup of butter. Number 2, if you make 5 cakes, how much butter did you use? So a half cup of butter equals 1 cake, so 5 times 1/2 equals 5 over 1 times 1/2 equals 5 halves. And if you put that back to a mixed fraction, you get 2 1/2 cup of butter. Number 3, if you ate 1/4 of 1 cake, how much butter did you consume? So there's half cup of butter in 1 cake, and you ate 1/4 of it, so that would mean we would be multiplying, so you would eat 1/8 cup. You would eat 1/8 of a cup of butter if you ate 1/4 of 1 cake. Number 12. In a recent election, 50% of female villagers and 30% of the male villagers who voted said yes to a community pool in the kingdom. What fraction of the voters who voted said yes to this? So 100% equals 10 out of 10, 50% equals 5 out of 10, 30% equals 3 out of 10, so 80%, and 50% plus 30% is 80%, so 8 out of 10, so 4/5 of the voters said yes to a community pool, to adding a community pool to the kingdom. Number 13. Matt decided he wanted to paint his room green. He has 2 identical sizes of yellow and blue cans. Each has more than 1 cup of yellow paint and more than 1 cup of blue paint. He pours 1 cup of yellow paint into the blue can and mixes it thoroughly. He sees that the green is not what he wanted. He put 1 can of his new green mixture back into the yellow paint and mixed it. Now he is happy with this new green color. Without doing any computations, which is greater, the percentage of yellow in the blue can or the percentage of blue in the yellow can? Explain using only carefully labeled math diagrams. So Matt and Kelly decided to just start with 3 of each color. We can see that over here. It's split into thirds, so then it even if there is more or less than 3 cups or 2 cups of paint for both colors, there will always be the same amount of yellow in red as there is red and yellow, because he started with the same amount and poured the same amount every single time. So no matter how many cups of paint were in each color, Matt and Kelly concluded that there would always be the same amount no matter which way you poured it, as long as you pour the same amount each time. Number 14. The Queen's car holds about 11 gallons of gas and gives her 30 miles per gallon. Use a double number line to answer the question below. How many gallons of gas are needed per week if she drives about 100 miles 4 times a week? How many times will she have to get gas for her car in a year? There's 52 weeks per year. And if she pays $2.50 a gallon, what is her yearly cost for gas? So Matt and Kelly decided to do cross multiplication. So there's 30 miles over 1 gallon, so 30 over 1, times 400 over x, because 100 times 4 is 400, so 400 miles over how many gallons? That's what we're trying to find. So 30x equals 400, so that would mean that there would be 13 1/3 gallons per 400 miles. So then how many times a week will she have to get gas? Or how many times will she have to get gas in a year? So if there's 13 1/3 gallons a week, and then there's 52 weeks in a year, you multiply, or you change the 13 1/3 back to an improper fraction, which is 40 over 3, multiply that by 52, and you get 693.3 repeating. And since, in this case, we can't really have a repeating decimal, they round it down to 693 times she would fill up her tank. Or get gas for her car in a year. Number 3, if she pays $2.50 a gallon, what is her yearly cost for gas? So 40 over 3 times $2.50 equals $33.33 each week, and there's 52 weeks in a year. So the Queen would spend about $1,333.33 in 1 year just on gas. Number 15. Kelly has 55 marbles in her toy chest. If she wants to share these equally between the King and Queen, how many marbles should each of them get? Solve using math diagrams. So Matt and Kelly decided to draw out 55 marbles and split them into 2 equal groups because Kelly wants to share these equally between the King and Queen. They found that there would be 27 in each group, so the King and Queen each would get 27 marbles, and there would be 1 left over. Number 16. Kelly has 55 marbles in her toy chest, And for her birthday, the king gives her a pack of 10 marbles, and the queen gives her 14 marbles. How many marbles does Kelly have now? So this is just a simple addition problem, and so Matt and Kelly did 55 plus 10 plus 14 to get 55 plus 24. So all in all, Kelly would have 79 marbles. Number 17. Matt and Kelly's teacher organizes a field trip to the Museum of Mathematical History in a neighboring city for her class of 20 kids. The school vans can hold up to 8 kids each. How many vans should their teacher arrange to make sure that all kids can go to the Museum of Mathematical History? So Matt and Kelly divided out 20 by 8, so they got 16 with a remainder of 4. And you can't really have a remainder of 4 kids, so that would be 3 vans. Oh no, so Matt and Kelly remember that division is just reverse multiplication, so they know that 8 times 2 is 16, and you need 4 more to get to 20 kids. So if 8 kids fits in 1 van, and 2 of the vans would give you 16 kids, they would know that they would need another additional van, so 3 vans total. Matt and Kelly had a hard day at school, learning all about the different parts of the numbers in their mythical math kingdom, but they do feel pretty confident now after learning all the different parts of numbers, how all of them work together on a number line, and just for everyday problems in general. They can't wait to tell their parents more about all the numbers that they learned in school, and can't wait to see how numbers play out in their everyday life. The end.